I'm not going to have you guys draw a bunch more Lewis structures where we can use the ones we've already drawn. But just understand that when it comes time for a test or a quiz, you'll have to start from the formula. Get the Lewis structure, and then get to these. Okay? The Lewis structures are just for us to figure out what to do. Now, what are we looking for? Well, that box, like it says at the top, we're looking for, and there's like 3 different phrases I'm going to use. That sheet uses electron regions. I'm perfectly happy with electron regions. Okay? Regions in which you're going to find electrons. You'll see or hear me say electron domains. Same idea, domain, region. Places where you're finding a lot of electrons, which means there's another phrase that you'll run into possibly, depending on what I've given you or where you read, electron density. So a place where there's a lot of electrons. It's dense in electrons. So for example, is this an area on this molecule that is dense in electrons? Are there electrons there? Are there here? No. Therefore, this would be a region of electron density where there are no electrons here. Okay, so domains, regions, densities, all referring to the same thing. When we do a Lewis structure, what we're going to be doing then is looking at the number of bonding pairs and the number of lone pairs. The sum of those 2 quantities, the number of bonding pairs and lone pairs around a central atom, are going to cause us to draw one of these 5 shapes. So clearly we're either going to have 2, 3, 4, 5, or 6 lone pair, bond pair sums. We're going to draw one of those shapes. Depending on the number of lone pair, however, if there are no lone pair, then the molecular geometry, the name of the shape of the molecule, is the same as what we drew. But if there's lone pairs of electrons, that's going to change the shape of that's going to change what we're going to name the positions of the atoms in that kind of structure. We're going to walk through a bunch of examples today, so you guys should be okay. But as you can see, as you go down each column, clearly with the linear, you can't do anything with that. But with the trigonal planar, we can have one of the positions occupied by a lone pair, in which case we would call the molecule, what name? Bent. With the tetrahedron, if there's one lone pair, what would we call that molecular shape? Trigonal pyramid. If there were 2 lone pairs, we would call it bent. Now notice that this bent is going to be different than this bent for reasons I'll get into here in a little bit. Trigonal bipyramid. If we have 1 lone pair, seesaw. Remember, there are a bunch of highly intelligent people sitting in a room coming up with these names. Seesaw. Did I go over how that can come about in this class? There might have been 1 or 2 people that were here for that. Where this is it, okay? Let's imagine all the positions are occupied by atoms except for where my hand is.
Didn't you draw that out in a certain way?
I didn't. Anyway, that's where they came up with seesaw. The old way of doing that would have been irregular tetrahedron. Which one do you want? Right. Now, if there's 2 lone pair, T-shape, well, I guess I'll just get rid of these, T-shaped, I think you guys can see why. And if there's 3 lone pair, linear. And then we can follow the same sort of reasoning for the... So do you guys see how that chart works out? You guys have to know those names. You will not have this chart available to you on tests or quizzes. All right. Next, let's talk about bond angles, or the positions of the atoms relative to each other. Anytime we're discussing a bond angle, it's between 3 adjacent atoms. What's the word adjacent mean? In a row, next to each other. Okay? So, clearly, there's only one bond angle here. Okay? So what is the XAX bond angle? 180. Yes.
On the quiz of the test, will you be using these pictures or will
You need to learn to draw these 5 shapes. Okay, trigonal planar. Pick an XAX. Let's go this one, this one, this one. Thank you. What about this one, this one, this one? Yeah, right. They're all 120. Okay. The tetrahedral. Now those two are pretty easy, right? The tetrahedral is going to kind of be a little wacky for you. It's not 90. Right. Okay, because of the three-dimensional nature of it. I'm not even going to have you guess because that would be pointless. So the XAX bond angle here is 109.5 degrees.
Yep, didn't guess that one. That's what I said.
Well, clearly it has to be less than 120. You guys get that, I hope.
I don't get that. Because then you'd have like 30.
Then I'd be back to this.
Well, I know, but don't you just have it coming out of a different angle?
Yeah, 109.5. That's the way they are as far away from each other as possible. Now, what about the XAX bond angle?
Oh, I understand now. All right. 52.735.
Yeah. And what about the XAX bond angle?
It's all the same.
Now, this is what I'm trying to do, is trying to get your brains to see that this is going behind the surface, this one's coming out of the surface. Okay, so do you see where I'm going with this? It takes a little while, but most people's brains can make that happen for them. So it doesn't matter. It's 109.5 everywhere. Yes. Oh, yeah. Absolutely. Okay, now, I'm going to guess that most of you are going to be able to figure these out. So I'm going to ask a question. Let's go, I'll do the easy one first. XAX. So this bond angle here is 90. Just for fun. Bless you. XAX. Still 90. What about XAX? Okay. What about XAX? We'll get there. We'll get there. Okay, just for fun then, what about XAX? 120. The triangle means it's coming out of the surface. The dashed line means it's going behind the surface. So, once again, watch. In fact, I'll put a marker on one of them so you guys can keep track of what's going on. So now the marker's on the same plane. You clearly see that, I hope, that that's 120. Okay. If I rotate this over to here, is that still 120? And if I put it back here, is that still 120? Doesn't matter where it is, as long as it's, by the way, let's get this terminology out of the way. These three positions are called the axial positions, like an axle. Okay? These three are the equatorial positions, like the equator. So that way when we're speaking to each other, because we're going to have to start talking about where the lone pairs are versus the bonding pairs, I'm going to say words like on the axial positions or equatorial positions. So all the equatorial positions are going to be 120, whereas all the axial relative to the equatorial positions are going to be 90. They have to be 90. And then, lastly, what's the only thing any of these can be?
90.
Right. Because...
Sure. Look at that bad boy. Just look at it.
Makes an excellent top.
Oh, I have a dreidel on.
I knew he was going to say that. I let it go. So, 90. I'll pick another one just for fun. Let's go 90 here. All right, here we go. Now, that's assuming that all those positions are occupied by bonding pairs of electrons. Now, remember, what is a chemical bond? I like to keep emphasizing this so you guys understand. When we're talking about a covalent chemical bond, what does that represent? What does that mean?
It means electrons being shared. There's like no polarity.
There's two electrons being shared between two that are being drawn towards two nuclei, and what's happening? Where are they being shared? An overlap of orbitals. Remember, we talked an overlap of orbitals, okay? And those two electrons are actually attracted to two different nuclei. And so I believe we did a thing, and I'm going to do it again, where we talked about that field of electric charge, and then depending on the electronegativity difference, in this case there is no electronegativity difference, so that's going to be very cylindrical shaped, okay, if you think three-dimensionally. If there is an electronegativity difference, then it might be misshapen a little bit. If that makes any sense. We've talked about that before, okay? But still being shared, still being drawn towards two nuclei. What about a lone pair of electrons? You know what? I don't want to use fluorine. That's a bad example. What about a lone pair of electrons? How many nuclei are they being attracted to? Just one. So remember that shape? We had that cylindrical shape, that tube kind of thing? Well, now that's actually going to be kind of transformed into something that maybe looks a little bit something like that. Does that make any sense? Why? Because both electrons are being drawn towards that one nucleus. That's going to come important in about 13 seconds or so. I'll take a risk. Go ahead.
So is that why you get bent shapes? Because electrons don't like each other, so you have them repulsing away from each other, and that's when you get the
No, it's bent because that's the positions of the atoms relative to each other.
Well, I know, but what about like for the triagonal?
Okay. Again, it's because these four atoms are oriented in a...
It has nothing to do with like electron repulsion?
No. Well, the fact that they're in the positions they're in is everything to do with electron repulsions. Remember, that's what the VSEPR thing was, valence shell electron pair repulsions. Okay? Hold on. Anyway, next. Thank you for not making a joke about that, by the way. Go.
On your paper, it says where the algebra is SE.
Yeah. That's Wednesday's lesson.
Okay, so
Okay, next. So I've got the base bond angles. Now, as I've been trying to emphasize, depending on the number of lone pair of electrons, not only will the name of the positions of the atoms be different than what is currently written up there, but the bond angles might change also because of that thing that I just showed you right there. Okay, but let's do a couple of examples before we do anything. Any questions before we move on? Yes.
What was the V thing? I was still confused.
What was what?
The V as
VSEP, valence shell electron pair repulsion.
so like
Say that 3 times fast. That. There we go. Okay, there we go. Valence shell electron pair repulsion. I'm just trying to help you out. You got it?
somebody else asked that.
Excellent. I swear she's the one that asked that. I swear she's the one. Wasn't she the one that just asked that? Okay, moving on. Please turn in your notes to the very first set of Lewis structures that we drew. It starts with methane, and then I believe it went to ammonia, then I believe it went to water, and then it went to probably carbon dioxide, and then possibly, I don't even know from there, ammonium ion or some such thing. Okay. There are many, many reasons why I start off with those molecules, one of which at the time I said, hey, these are things you're very familiar with. Let's look at these. The other reason is they're great examples for introducing this whole idea of applying the molecular geometry to. Okay? So, you've already got the Lewis structure drawn for methane. This is what you drew. You do not have to draw it again. You already have it drawn. On a test or quiz from this point forward, you will not get any points for drawing that. However, this will lead you to what you will get points for. How many electron regions are about the central atom? 4. What is that going to make you draw? A tetrahedron. So you're going to draw a tetrahedron. You're going to go boom, 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 and boom. You're going to draw that. So go ahead and draw that. I don't know. So you get 2 points for making that three-dimensional drawing. Nicely done, everyone.
Does it matter in what orientation, like
draw that.
I know, but like
draw that. That was kind of fun. Now, how many bond pairs are there? 4. How many lone pair? 0. So what is the name of the molecular geometry, or the positions of the atoms relative to each other? Tetrahedron. Whatever. All and whatever. I forget what your paper says. It doesn't matter.
I just wanted to make sure.
Yeah, it doesn't matter. Okay. Just out of curiosity, what is the hydrogen-carbon-hydrogen bond angle? 109.5. You have just gotten 4 of the 6 possible points available. You don't know about the other 2 points yet. How are we doing so far? Great. You draw, 2 points for the drawing, 1 point for indicating the molecular geometry, another point for determining the bond angle. Next, let's do ammonia. You already have the Lewis structure drawn. The Lewis structure for ammonia looked like this. It really doesn't matter where you put what, but you guys did something similar to that. Okay? How many pairs of, or how many electron regions are there? How many electron regions are there? 4. What are we going to draw? Tetrahedron. We're going to draw a tetrahedron. However, only 3 of those positions are occupied by atoms. The other one is occupied by a lone pair of electrons. Pardon?
You were just talking about the positions, right?
Right, there were 4.
No, because you just like the names of them.
Not sure what you're talking about. We'll get to it. We'll get to it. All right. Now, because there is a lone pair of electrons, what is the name of the positions of the atoms relative to each other? Trigonal pyramid. Yes. Oh no, it comes into a lot of play when we get to the polarity piece that you don't know yet. Okay? So there we go. So once again, 6 points. You get 2 points for the correctly drawn structure. You get a point for identifying the molecular geometry, and you get a point for identifying the bond angle. Oh, but wait. Remember, these 2 electrons are attracted to 2 different nuclei. You don't have to draw this piece right now. So therefore, they're spread out between the 2 relatively evenly, even though there is an electronegativity difference. So they're going to spend a little bit more time with the nitrogen than they are the hydrogen. But what about these 2? They're only drawn to 1 nucleus. So what did that do? It kind of spread that out a little bit, which starts to interfere with the electron pairs that are here, repelling them a little bit. So what's going to happen to the angle between the 3 atoms? It is going to change in what direction? Decrease. Okay? So, lone pairs are going to modify the standard bond angles. In this case, this bond angle is going to be, as you just determined, and you only have to know this, less than 109.5 degrees. You're welcome. And the reason the reason I'm not giving you a number there is because that decrease is going to vary depending on the atoms that are actually there. Okay? But we definitely know it's going to be less than 109.5. So we're going to stick with that. Yes?
So will the angles always be 109.5, 120, and 90, and then it's just a matter of knowing equatorial and axial?
No, it's going to be a matter of whether they're going to be modified by lone pairs of electrons. That has nothing to do with equatorial axial because in a tetrahedron there is no equatorial and axial. Okay. So, once again, 4 points, 2 for the drawing, 1 for the name, 1 for the bond angle. Next, just for fun, would you guys like to try, what's the next one? I believe it was water. Would you like some? Would you like some? No, I'm just kidding. Go ahead. I'm going to let you guys try water on your own. Hey, if you screw it up, you screw it up, okay? But I just want to see if you can start putting things together. For your water Lewis structure, how many bond pairs did you have? How many bond pairs did you have? How many lone pair did you have? For a total of, there we go. So what are you going to draw? You're going to draw a tetrahedron. You're only going to draw 1 of 5 shapes.
Wait, is it tetrahedron or tetrahedral?
Yes.
Yes, it does.
Depends on what source you're looking at.
Okay. Oh no,
It is in the shape of a tetrahedron. However, it has a tetrahedral shape.
So.
Right. It's the same.
Oh, so tetrahedral is just the adjective.
There you go. Boy, I'm going to overstep a little bit here, but that's okay. So, when you guys drew your Lewis structure for water, almost all of you drew something that was incredibly closely related to that. And now we're looking at going, okay, hey, there's 4 electron domains, 4 electron regions, so I'm going to draw a tetrahedron. Now, because I've got a little bit more experience than you guys do at this, I know where we're going a little bit later. So I'm going to put my hydrogens here. I know you probably didn't do that. That's okay. Okay? Now, it's okay if you didn't do that, as long as you had the original diagram and replace 2 of those areas with a lone pairs. Now, I'm going to go out on a limb here. First of all, what is the name of the molecular geometry? Bent.
I did it.
Okay. And what is this bond angle?
Less than 109.5.
But so is that. Is this different than that? So how are we going to handle that?
Greater than.
What's that? Ding, 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 ding.
I thought that first was a messed up joke, then I decided not to make it.
Yeah.
Oh, really?
Well, we're not going. Okay.
Well, what do you think?
Now we have a linear, right?
Yeah.
So no, we can't do 3.
Oh, okay.
Now listen, back up here, I never did give it to you. The actual, for ammonia, you don't have to write this down, you don't have to know it. I'm just saying, there is a value. For ammonia, it's 107. Okay, but as I was saying earlier, depending on the molecule, that might be something different than 107. So I'm not going to have you know that. But less than 109.05 is clearly what it's going to be. Over here, clearly going to be less than 109.5, because now we got 2 lone pair doing the same thing that we talked about up here. Okay. So are you guys making these little notes on your little sheets or in your notes? I don't care which. It really doesn't matter to me. Okay, let's try this, because these were your next examples, I believe, or they were really soon after. I'm not going to do the NH4 because that's not going to get us anywhere. I'm not going to. We can do that one.
And then SO3.
We can do this one because that'll kill a couple birds with one stone. And I would like to do. Oh shoot! I was going to go somewhere with that water. I'm going to go back to the water later. I can't read here. Where? Oh, there it is. There it is. SCl4 1 plus. No, it's just FCl4. Okay. Okay. So these were all examples that we did for your learning how to do Lewis structures. So if you could refer to those and then go to the molecular geometries. What double bond? It's not there.
So we don't have to draw it?
Well, sure. Remember we talked about the resonance? Resonance?
Oh, the resonance structure? I thought you said residence. I was
No.
I don't know.
What is the bond order for nitrate? My bad, I forgot where you guys are. NO3, 1 negative.
Is the angle for nitrogen for the ammonia and Is it 107 because nitrogen is 7 on the periodic table?
Yes, yes. I don't know what pH is supposed to look like.
I thought it was pretty close. I thought that was like...
That whole free association thing again? No.
Okay. I may or may not have gotten it.
That's okay. That's okay.
I'm feeling lucky and it's emergency.
Good luck. I don't even know what that means.
Linear?
Okay. Now, when you guys drew your carbon dioxide, on your Lewis structure, you guys had all drawn this, probably fairly accurately without even trying. Is that what you guys all had for your Lewis structure? Okay, here's the question, and I know this may have concerned some of you. How many electron regions around the central atom?
4.
Okay, let me try this again. How many electron domains? Same question. Trying to find the words that match up best for you. How many regions of electron density?
4.
Wait, I don't know.
2. There's electrons here. There's electrons here. How many electrons are here? How about here? So, how many electron domains or regions? 2. Multiple bonds are a region, is where I'm going with this. Okay? So we got 2 regions. Therefore, what are we going to draw? Linear. What are we going to name it? Linear. And what is the bond angle? 180 degrees. Yeah, you're done. It's over.
Does it matter?
Oh. Wait.
Yes.
Does it matter where you put the electrons?
Again, if you haven't figured this out yet, we're trying to get the electron pairs as far away from each other as possible. Yes.
Mr. Lemon, do you draw the double bonds then when
Yeah.
you're doing this?
Yeah.
Okay.
So would you like a double triangle?
It's going to look just like that. What's that again?
Like if you had it coming forward, would you like a double triangle?
What are you saying?
Oh. I understand what you're saying, but I don't know if we'd ever have to do that.
It would look like this. Because all you'd see would be the tip of one oxygen.
No, it's like
No, like not with carbon dioxide, but with
Oh.
some element where you had.
Like a trigonal plane.
I don't know. Let's find out. Okay, nitrate. You guys ended up drawing something. When you guys did it, probably drew something similar to this. When you guys did it for your first Lewis structure, you probably came up with something similar to that. Would you agree? Okay. With that being said, how many electron regions are there about the central atom? 3. Here, here, here. Yeah, just let it go. Just let it go. There's 3. So what's that going to make us draw?
a trigonal
Planar. So we're going to draw a trigonal planar. Now, what is the name of this molecular geometry? Trigonal planar, because there's no lone pair of electrons around the central atom. And what will be the oxygen, nitrogen, oxygen bond angle? 120.
So how are you supposed to do the lines in the triangle?
I'm not going to.
Oh, I was thinking of a touch efficient.
I know.
How would you do the lines in the triangle?
Just like I've shown you. Just like it.
So I know for a double bond, how would you do it? Would it be 2 triangles?
No. Okay. What's the next one? SCl4?
Yeah.
Okay. So when you guys drew the Lewis structure for this, you ended up drawing something that looked like this. Or some such thing. You had an extra pair of electrons that you put around the sulfur. Okay? Listen carefully to this, because this is the first time we've run into this. How many electron regions about the central atom? There are 5. What is that going to make us draw? Yep.
This is the one you drew at the very beginning. And you don't need to write it down.
Whoops. Now, there are specific places that you can put the lone pair. And I'm going to tell you what those specific... That is a really, really bad triangle.
I don't think that was even a triangle. 4-sided.
That's even worse.
That one was better.
There we go. I'm happy with that. All right. Anyway, the lone pair of electrons, because they take up so much space, they are going to not be in positions where there are 90-degree lone pair bond pair interactions. Okay, let me demonstrate what that means. Okay, so you're trying to put the lone pair of electrons to reduce the number of lone pair bond pair interactions. If I put my fingers on a lone pair of electrons, how many lone pair bond pair interactions would there be? 3. If I put the lone pair here, how many lone pair bond pair 90-degree interactions would there be? 2. 1 here, 1 here. If I were here, if I had the lone pair here, there would be 1 here, and 1 here.
Does that go for all interactions or just 90?
This is what I just said. 90. So, where am I going to put the lone pair of electrons? On one of the equatorial positions. Just because it's going to make, I know that it's going to make my life easier later, I'm going to put it there. So, I don't know what I do with my marker. What was it, chlorine? Boom, 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 boom. And as Jared just said, because there is one lone pair, what is the name of the positions of the atoms? Seesaw. And what are the bond angles? Well, what's this one going to be? 90. Just for fun, what's this one going to be? Still going to be 90. And just for fun, what is this one going to be? You could, yeah, there's debate on this one. You could go with the 120. Theoretically, it could be less than 120. Well, you can do that if you want. You can do that if you want. There's debate as to whether the 120 is close enough for that lone pair of electrons to really have that much of an influence. Because honestly, we went from what, 109.5 to 107. Really small change in bond angle, right? And that was at 109.5. Now we're at 120. We got a whole another 10 degrees. Yeah. I mean, I'm not gonna. So as Rena just said, you can go without. You can do that. That's fine. Either way. Yes. I don't care. The hooded one.
Well, I forgot my question.
Okay, Bobby.
Would you take off points if we wrote trigonal bipyramid instead of seesaw there?
Absolutely, because the name of the molecular geometry is not trigonal bipyramid, it's seesaw. Because there's a lone pair of electrons. Yes?
How will we identify which degree this of?
Oh! Well,
I'm still kind of confused with
Yeah,
what the
which
90 degree does and what 100.
well, let's look. What positions are these in? Equatorial. And how are the equatorial positions related to the axial positions? Here, Reno, I'm going to throw this up. This is why I'm doing this, so you guys can see it. So here's the lone pair where my fingers are. What is this relationship? What about this relationship? And I think I did this one. 90. What's this relationship? 120 or less than 120.
Can I come after class and just see you do that because I can't see anything.
Okay. Okay. Or you can sit there.
Uh,
Okay. I'm just saying. I'm just giving you options. There's options. Yeah.
I meant, like, will we write out all the angles?
No. So the question would be something like all pertinent angles. Now, really, this is the only one that it really matters. If you guys think about it, this is the only one where there's two options. Everything else, they're all the same. Hey, listen. The second set of Lewis structures that I had you guys draw, I believe it started with ClO3 1-. Does that sound familiar? ClO3 1-.